Okay, so lecture 8.2, constrained linear optimization. Consider a linear objective function, f, mapping Rn to R with variables xi in vector x and coefficients ci in vector c, such that f of x is c dot x, as in equation 8.9, subject to the linear constraints, restrictions on xi, that matrix A times x, all of those are less than or equal to vector A. B times x, matrix B times x is equal to vector little b. So these are equality constraints. So these are inequality constraints. Gotta get my pen out here. Whoa, that wasn't supposed to happen. Not sure why that happened. Okay, so these are inequality constraints, and these are the equality constraints. So you can say, okay, this expression in x has to equal exactly this, whereas here these are constraints that are inequalities, saying that this expression has to be less than or equal to this other expression. And finally, this is bounds on x. So each of these variables xi has a lower bound and an upper bound. Okay, those bounds could be infinity. Okay, so A and B are constant matrices, and A, B, L, and U are n vectors. This is one formulation of what is called a linear programming problem. Usually, we want to maximize f over the constraints. Such problems frequently arise throughout engineering, for instance, in manufacturing, transportation, operations, etc. Really, anytime you're seeking an optimal design, which more and more we keep pushing the envelope of technology and we want an optimal design. Something that works is not going to cut it in a highly competitive technology environment. So you have to optimize. They're called constrained because there are constraints on x. They are called linear because the objective function and the constraints are linear. Okay, and it turns out we're going to use this linearity. So whereas in the previous method with unconstrained optimization using gradient descent, we didn't require that the functions were linear. Now we're requiring that they be linear, and we're going to use that linearity to help us solve these problems. We call a pair x and fx for which x satisfies equation 8.10, so the constraints, a feasible solution. Of course, not every feasible solution is optimal. A feasible solution is optimal if and only if there exists no other feasible solution for which f is greater, assuming we're maximizing the function. We call the vector subspace of feasible solutions S. Okay? So you can think of 8.10 as carving out some region in Rn that is the solution subspace S. Okay, so that's where we're looking for values of f that are greatest. So that's the problem. This comes up very frequently, and it's a very well understood problem. It's been studied for over 50 years now. It has a lot of good solutions. So we'll talk about that. Feasible solutions form a polytope. Consider the effect of the constraints. Each of the equalities and inequalities defines a linear hyperplane in Rn. In other words, a linear subspace of dimension n minus 1. Okay, so let's stop for a second and think about what a hyperplane is. So if you're in R2, a hyperplane is a linear subspace of dimension n minus 1. So x1, x2, a linear subspace of dimension n minus 1 is a line. Okay, so these are all linear subspaces. Okay. Now, if you're in R3, say x1, x2, x3, then it's a plane, right? That was predictably not awesome to do my plane that way, but it's a plane. Okay. That's of dimension 1 less than the space. It's linear, it's flat. Okay. So, and then in R4, R5, etc., you just drop down 1 dimension and you have a flat space. It's hard to visualize when you go up from here, right? If you go to R4, it's a volume that's a hyperplane. Okay. If you go down to R1, what's a hyperplane? A point. Yeah. Okay. So there's our hyperplane concept. So each of the equalities and inequalities defines a linear hyperplane in Rn, either as a boundary of S, which is the case for an inequality constraint, or as a restriction of S to the hyperplane. So if you think about a constraint, we're used to thinking about them in R2, right? You might say that one number times 5 plus the other number has to be less than something, right? And that's going to define some line here, and it's actually going to define, that's going to be the boundary of the region that's valid by that constraint. Now, the line, though, is the hyperplane. It's either going to be the boundary, or it's going, if you have an equality instead of an inequality. If you have an equality, you're saying it doesn't have to be, like, say, less than. It has to be equal to, so it has to lie on that line. Okay? When joined, these hyperplanes are the boundary of S. Equalities restrict S to lower dimension. Okay, so if you have R2 and you say that there's this equality constraint that x1 plus 2x2 equals 5, you've just restricted S to a line in R2, not a region in R2. So you've dropped the dimensionality of your S, your solution subspace. So we see that each of the boundaries of S is flat, which makes S a polytope. In R2, a polygon. So a polytope is the generalization of a polygon. So in the plane, we're used to seeing polygons like that, right? Well, if you go up to higher dimension, there's a polygon-like thing. So in R3, a polygon has flat faces. That's not flat looking. Jeez, I cannot draw a straight line there. So that might be a polytope in R3. Okay, it's got flat faces on it, or you go to higher and higher dimensions, flat volumes, and etc. What makes these especially interesting is that polytopes have vertices where hyperplanes intersect. Okay, so in in R2, we've got, say, two hyperplanes, and they intersect at a vertex of the polygon. Those two intersect at this vertex. So you have these vertices, okay, where the hyperplanes intersect to define your S, your solution space. Now remember, just finding something in the solution space is not really the point. We want to find the optimal solution in the solution space. These are just possible optimal solutions, all of them. Okay, what makes this especially interesting is that polytopes have vertices where hyperplanes intersect. Solutions at the vertices are called basic feasible solutions. Okay, so the vertices, there are obviously way fewer vertices than there are points inside that region, right? So those vertices kind of define that region. And in a moment, we're going to find out that those vertices are really the only thing that matters. Okay. Our objective function, f, is linear. So for some constant h, f of x equals h defines a level set that is itself a hyperplane h in Rn. Okay, so thinking back to our R2 space here, we have a linear function f over x1, x2. So you could think of that as being like the third dimension coming out of the board, if you will. And what does a linear function of two variables look like?
ax1 plus ax2 equal to constant?
Yeah, so if we were to do a three-dimensional plot, it would be a flat surface. It would be a plane that's in R3, right? And if you were to think of some constant value of that function, then a constant value of this plane is going to just be a line in R2, right? It's going to have the same value for a line in R2. So this line would be a constant value. This line would be a constant value. This line would be a constant value. Okay, so these are all constant values of f. Okay, so anywhere in the solution region here, if you were to take this point or this point or this point or this point, all those points are going to have the same value of f. Remember, we're looking for the maximum value of f. Typically, these are maximization problems, but maximization, minimization, all you have to do is flip the sign to change it, so it doesn't really matter that much. Okay, so good. If this hyperplane intersects S at a point X, such that we have a solution x, f of x equals h, is the corresponding solution. There are three possibilities when h intersects S. So remember, h is the hyperplane corresponding to a specific value of our function f, right? Of our objective function. And we have, so some of these are not going to intersect at all, right? So some of these hyperplanes are going to miss, say this is our region, are going to miss our region completely. We're going to miss S completely. But when S does, or H does intersect S, so these are H, this is S. So when H does intersect S, we have three possibilities, okay? So that intersection we'll put the intersection in green. That intersection can be just at a vertex, okay? So which one did I list first, actually? Yeah, so h of S is a vertex of S. So in this case, So if we have this H here that goes through that vertex, then the intersection right there is H intersect S in green. Then we have a vertex that is selected. Another possibility is like this H, that the intersection is touches an interior point. Well, I skipped the second one, which this region doesn't actually do it justice. But you could imagine that this line, say this boundary, happened to be parallel with this line, and you go through multiple vertices. Okay, so you go through you go along one of the boundaries. So it could also be a boundary. In the direction I've been drawing these H's, it wouldn't be, but you could potentially be touching the entire boundary with one of these lines. The next possibility is that your intersection goes through the interior of the region of S. Okay? Your intersection could be part of the interior region. Okay, so let's inspect that last case for a moment. Okay. If H intersect S is a boundary, that's the second possibility. The third possibility is that it slices through the interior of S. This third option implies that there exists a level set G corresponding to f of x equals G, such that big G intersects S and little g is greater than H. Okay? So solutions on H intersect S are not optimal in this case. So that's this situation. What we're saying is that for this problem, if your hyperplane goes through the interior of this region, then there exists another hyperplane that's actually going to give you a better solution. Okay? I have not proved that in this case. I'm just trying to give you guys, I think it's kind of motivated by seeing that, okay, you could move it to a corner point and you're going to have a maximum at probably one of these corner points. Because we have a linear f, right? F is going to be some plane in R3. It's going to be some plane that, there's going to be some hyperplane that has a value that increases in some direction, right? And if it's increasing in some direction, then if you're going through the interior, you can move it in some direction, which is always going to have a greater value. This has been proven rigorously. I'm just trying to give you guys like an idea of why this is the case. So what this means, we conclude that either the first or second case must be true for optimal solutions. Okay? So that's important. So we said that, so if we're going to have an optimal solution, this can't be the case. Okay? And notice that in both of the cases, here and here, a potentially optimal solution occurs at least one vertex. At least one vertex. So in this case, we have a solution that follows a boundary of the hyperplane. But the boundary is going to have vertices at the ends of it, right? And those vertices at the ends are going to have the same level set, or the same value h, little h, okay? And so if it's optimal, then they're both equal. So they're both optimal solutions. So that means, taken together, that the key insight then is that an optimal solution occurs at a vertex of S. Okay? Which is very good news. This means we don't need to search all of S or even its boundary. We need only search the vertices. Okay. That's good. Helpful as this is, it restricts us down to n choose the number of constraints, potentially optimal solutions. Usually still too many to search in a naive way. Okay, so this, once you have a bunch of constraints and you have a lot of variables, this becomes intractable to just exhaustively search. Okay. In lecture 8.3, this is mitigated by introducing a new powerful searching method. Well, the method isn't really very new, but I drew this because I was starting to draw all those figures that I drew above sketching. I was going to do that in TAKZ, but I didn't get to it. So, all right, so this is just a fun little drawing right now. Isn't it cute? It's cute. And look at this.
What does this point represent? Like the eye is looking somewhere?
I'm trying to show in R2 the intersection of two of our hyperplanes, and then this is the region. This is S. This is our, and I'm just trying to show one part of it. I don't want to show the whole polygon, but just S. And then I was going to show lines going through it, and actually what I was going to do is I was going to show these lines. Lines parallel to this, and then there's one that crosses there, or one that follows this up, and then one this, and so we could see all the possibilities. So that's, I don't know. Hopefully I get to that. But for now, it's just cute. Okay. All right, so that's all I've got for this overall understanding of constrained linear optimization.